Let's take a look at another problem here. Find the ones digit in 3 to the power of 99. Now, if you get a calculator, we're not going to be able to figure that out. I'm not sure the calculator will do it. The number's so big. However, looking at a pattern, right, we could then maybe predict. How would we do that? Well, let's take a look. 3 to the power of 1 is 3. And so you can see my sequence of powers of 3. Notice 3, 9, 27, 81, 243, 729, 287. So using this thought process here, we could probably predict 3 to the power of 8, whatever it is, whatever the number is, right? Whatever that number is, I think we can predict that that last digit for 3 to the power of 8, 3, 9, 27, 81, 3, 9, 7, 1, 3, 9, 7, 1, somehow this last digit has to end in a 1. And so what that number is probably 6,000 and something, but it's going to end in a 1. So to me, it looks like anything that's a multiple of 4 always ends in 1, if you look carefully. Any multiple of 3 ends in 7. So if 3 to the power of 100, its last digit I would predict is a 1, because 100 is divisible by 4. And then 99 is divisible by 3, so my prediction is the last digit would be a 7 based off that pattern there. And so what we're looking at is really looking at a sequence of numbers, and that's what a pattern of numbers arranged in some order is called a sequence. Each term in the sequence, right, each number is called a term. And the way we write it, you'll see an ellipsis, dot, 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 meaning it's going to continue in the same pattern. And this here, these sequences are very famous sequences in mathematics. Another famous sequence, the Fibonacci sequence, I would look that up just to get a sense of the application in the world, but it's just 1 plus 1 is 2, 1 plus 2 is 3, and that's how this sequence is created. And so you have these other sequences. And what we're looking at here is something called inductive reasoning. Whenever we're thinking mathematically in the sense of patterns and looking at patterns to make conclusions and make predictions, draw conclusions and make predictions, we're using what's called inductive reasoning to solve a problem like that. Inductive reasoning, a way of thinking using patterns to make predictions, right? You would say I'm using inductive reasoning. Let's look at another example here. Again, these are longer examples, so I'm going to get to the solution, but if you, more importantly, out of these problems is your strategies and thinking about how to solve them. They do take longer to solve, even though I'm presenting the answers for you. And so in a case like this, we want to make a list of values here. The solution to the number 10 can be expressed, right, as the sum of 4 odd numbers in 3 ways. There it is. How many ways can 20 be expressed as a sum of odd numbers? That would take some time, but what happens is you can start with this first 3, a smaller problem, and then out of those, notice I highlighted these sums here, you can then build. And so what ends up happening, here's your list here, but what ends up happening is you'll end up kind of just making a systematic list to solve a problem like that, right? And that becomes an effective strategy of effective mathematical thinking, is to kind of make some list of values. Just like on the next problem here of you have 3 darts, these are your points, and again, that's a game where you throw a dart at a board and wherever you hit it, you get those points. Here's the points system. And then the question is, what are all the possible scores? And so I started making a list here. And so you can see and think about, well, what would be the next thing? Well, 0, 0, 0, 0, 0, 1, 0, 4, 4. And so another possible set of numbers in this case would be they could get 1, 1, 4, right? That could be another possible score, 1, 1, and 4. But the list, this is not an exhaustive list, meaning there's still more. Here are kind of the answer to that, but you can see all the different point totals, but using a list to do that is important there.